Okay, it's time for us to continue. And today is the final lecture for the second part, electricity and magnetism. Today, what we are going to do is, in the first part, we are going to basically finish the remaining topics about magnetism. And then in the second part, I will give you a summary lecture, try to highlight the key concept, what we have discussed, and also equally important is the typical question that we are going to test for each of those key concepts. So pretty much this is what we need to finish today. And for the review of the last lecture, because later we are going to have this overall summary, so here I will just skip the review about the magnetic field, basically the topics we discussed last week, and we will just directly go to the new topics for today. And the first new topic is the so-called Faraday's law. And the Faraday's law basically is a description of the magnetic field generate a current. In the last lecture, if you still can remember, we have this so-called Biot-Savart's law to quantify B generated by I. That is from I to B, right? And today, the so-called Faraday's law is opposite, from B to I. Sorry, here just now is I to B, from I to B. And today, this Faraday's law is opposite process, from magnetic field to a current. And this is a so-called electromagnetic induction. This from B to I is a so-called electromagnetic induction. And something you can kind of visualize this electromagnetic induction process is this kind of experiment. Let's say if you have this kind of coil connected to an ampere meter which can read the current flow through this coil. And of course, if you don't have this magnet, or you don't have anything else, you don't have a battery, then the current flow inside this coil, of course, is always going to be zero. One way you can generate certain current, of course, you can, let's say, connect everything to a battery, then you can generate certain current flow inside the coil, right? And another way you can generate a current flow is by moving a magnet. Let's say this kind of magnet, basically there are two sides, North Pole and South Pole. And when you move this magnet with respect to this coil, then you will find out you can get a finite reading. That is to say, when you're moving this magnet, you are generating a certain current flow inside this coil. This is basically what you have initially is a magnetic field due to the magnet. While you are moving the magnet, what you get is this current flow inside this coil. So you can see here you have a conversion from magnetic field to a electrical current flow. So from B to I. And this is, again, the so-called electromagnetic induction. And actually, this is something you should have experienced or you have been using in your daily life. If you do something, if you have ever used this kind of so-called induction hob. Of course, the most common one, the gas hob, is you have this fire from gas. But inside this kind of induction hob, what happens actually is at the bottom of your hob, you have this kind of coil. You have this kind of coil, and at the same time, you can generate a current, let's say, supplied by the power. Let's here. Of course, because what you are having, typically the current flow you get from the wall plug is a so-called AC current, meaning the magnitude is changing. As a result, you will induce a current flow inside this kind of coil. And of course, that is how you get the heating effect. Once you have this current flow inside the coil, then it will heat up. It will heat up, right, due to this kind of thermal generation. Basically, it's completely different kind of heat generation. That is why when you are using this kind of gas hob, for sure you know immediately, let's say you turn off the gas, you still cannot touch this, right? It's still super hot. But for this kind of induction hob, actually, immediately you remove this pan, you touch this surface, it's still not so warm because of this kind of different heating mechanism and different heating process, right? This is something actually we have been using for this electromagnetic induction. Of course, for us, what we are going to do today is to establish the principle and also how we can quantify this kind of conversion from B to I. And first of all, the first parameter we need to define is the so-called electromotive force, typically written in short with this EMF, electromotive force. And this Faraday's law tells you there will be an induced EMF in a circuit when the magnetic field through the circuit is not a constant over time, or it changes with time. When you have this kind of time-varying magnetic field, and then you will induce an electromotive force inside this loop. So here, first of all, the so-called electromotive force, to put in a simple way, you can just understand it as a voltage or potential difference. So this electromotive force is just something like the potential difference or voltage. At least within our course, these two are pretty much the same. Of course, strictly speaking, they are not exactly the same. But for us, you can just consider them to be the same parameter. So this is the electromotive force, and this electromotive force is non-zero when you have this kind of time-varying magnetic field. And if you put this in a formula, basically the so-called EMF typically is written with this symbol, this epsilon, E equals to this d phi b over dt. The phi b is just the magnetic flux. This d phi b over dt basically means the time rate of change of magnetic flux. So here is a bit awkward, this time rate of change of magnetic flux. So this is the meaning of d phi b over dt. And of course, this phi b magnetic flux, this is how you determine the magnetic flux for any surface, right? The magnetic flux. And if you still remember, if we do this integration for a closed surface, what would be the result? The flux, the magnetic flux for a closed surface, it should be how much? Still remember? Zero. Still remember why 0? Theta equal 90. Well, you can say in that way, if you based on this formula, these two must be perpendicular. But another more physically straightforward way to understand, if you remember, we say this is because of this fundamental feature of any magnetic field. This north pole and south pole NS always come in pair. You cannot separate to only have, say, north pole or south pole. This is the first point. And the magnetic field line, second, always leaving north pole and coming back south pole. So because, again, north pole or south pole always come in pair, so actually the magnetic field line is always a loop. So if for this kind of loop wire, you have another, let's say, any kind of arbitrarily closed surface, you will find out the same electrical field, the same magnetic field line will enter the loop at one point and leave the same closed surface at another point. So that is why for any closed surface, the same magnetic field line first enter and then leave the surface. So that is to say the number of net magnetic field line penetrating through the closed surface must always be 0. And the meaning of net magnetic field line penetrating through the surface is the magnetic flux. So that is why for the magnetic field you always have this. But of course here, because we are not necessarily talking about a closed surface. It can be an open surface, and if it's for an open surface, then this integration not necessary to be 0. Remember this integration, this is valid only for closed surface. For an open surface, the flux can be non-zero. Right. So this is the definition and also the formula by definition. And if we follow this simple formula, then of course we can tell when you can have this finite EMF. That is to say this epsilon being non-zero. Of course, all you need to look at, if you want this to be non-zero, that is to say, again, this phi b cannot be a constant over time, right? It must be keep changing as a function of time. And how can you have this phi b being not constant? You can have this b being changed with time, or the surface area of the loop being non-constant, or the angle between these two vectors, or any combination of the above. So you can, it's quite straightforward. Again, all is just to say you need to make sure this dot product being is not a constant. That is the only requirement. You will get a finite EMF, right? And this is the case. This is a simple formula. Typically, when you only have one loop. And if you have multiple loops, especially if you have n the same identical loops, and overall the total EMF is going to be times a factor of n. That is to say, the so-called n identical loop, basically, if you look at here, if you look at this coil, basically you have 1, 2, 3, 4, 5. If you count this, then in total 6 loops. So that is to say the total EMF induced in this coil, you will need to times this coefficient of 6. N equals 6 in this case. So this is the so-called this factor, how do you consider this factor n? So far, is it all clear how we can generally determine the induced EMF? By definition, just to determine you have a loop, all you need to figure out is how the magnetic flux through the loop is changing as a function of time, as a function of time. And if we try to look at this very simple question, to apply this definition to figure out the induced EMF, first, a coil with 210 of wire, that is to say in this case, this capital N is 200, and each turn is given is a square of 18 centimeter. So from here, you can find out the A for each turn, right? And you have a uniform magnetic field directed perpendicular to the plane of the coil, and the magnetic field changes linearly from 0 to this finite value within this 0.8 second. Ask you to determine the magnitude of the induced EMF, right? So you can see what you have is a magnetic field that is changing within this time period, 0.8 seconds. So all you need to do is to figure out the initial magnetic flux and the final magnetic flux, right? The magnetic flux at t equals 0 and magnetic flux at t equals 0.8, right? So then you can get the magnetic flux, the change of magnetic flux, right? So in this case, because it tells you initially B is 0, of course, then the initial flux is 0, and all you need to find out is the final flux, the magnetic flux at 0.8 seconds, right? And you can get this one. So initial flux and the final magnetic flux, and then the change of the magnetic flux, and also the time variation. And finally, times this factor n will give you the total induced EMF. So it's going to be a voltage. Right. Yes? Which one becomes negative? Here? This one actually doesn't matter, depends on how you are defining this induced EMF. Yes, it's going, again, this one is something like potential difference. So the potential difference, if you define it to be, let's say, A minus B or B minus A, it's just one being positive, one being negative. Any other questions? No? Okay. Then we can move on to the next one, the so-called motional EMF. Again, so far what we have discussed is a kind of general picture of electromagnetic induction. It applies to any scenario. Whether it's this kind of linear change, or in principle, it can be any kind of change of magnetic flux. So this is a general picture. And here we have a more specific or special physical picture of the so-called electromagnetic induction. That is the motional EMF, which tells you you can also have a finite EMF when you have a moving conductor inside a magnetic field. So here the component is first a moving conductor, second external magnetic field. As long as you have these two, you will also have a finite EMF. So you can see, pay attention to the difference. In this case, actually, there is no closed loop. That is to say, actually, you cannot clearly determine this magnetic flux anymore. You only have a conductor, it's not a loop. But still, there will be a finite EMF. And the way we understand this kind of motional EMF, the fundamental physics actually is nothing, there's nothing new. What happens, let's say if we look at this kind of scenario, where you have this kind of external magnetic field. So when you see this an array of cloth, what does it tell you in terms of the direction? It should be pointing into the page or out of the page. This kind of notation, it should be into the page. If it's an array of dots, then it's pointing out of the page. Again, this is just a convention. You can say you have to memorize it. There's no reason why it is defined in this way. So cross means pointing into the page, dot means pointing out of the page. So this is the first. And within the magnetic field, there is this kind of conductor. This is a conductor. It can be a wire. And when you move this conductor, let's say give it a finite velocity v along this way, eventually you will build up a finite EMF at the two ends of this wire. This is a so-called motional EMF. So now let's try to decompose this motional EMF. First, again, there is a magnetic field. This conductor, inside the conductor, what do you have? Let's say typically inside a metal, what do you have? You have a lot of free electron, right? And you have a free electron. Let's say if you look at this electron, if this entire conductor is moving with this velocity v, then effectively this electron itself must also have this the same velocity v, right? So now you have a moving electron inside a magnetic field B. So what will happen? A moving electron inside a magnetic field B. A moving charge inside a magnetic field, what will happen? There will be a magnetic force on this charge, on this electron, right? And this is how we can quantify this force. The magnetic force on single moving charge. Now, the charge, let's say we just talk about electron, is going to be this minus E. This is the Q, right? So now, based on this formula, you need to determine the direction of the FB. How do we do it? So, okay, you tell me where is this FB in this case, based on the V and the B. Again, the way you do it, use this right-hand rule. This is going to be the first vector V, second vector B, and this is going to be V cross B. So the way you do it is going to be V, B pointing into the page. So this is a V, this is a B, so this is V cross B pointing up, right? So V cross B is going to be pointing up, and now we are talking about a negative charge. So you need to reverse V cross B to get FB, right? Again, remember this just gives you the direction of V cross B. Whether this is the same as FB or not depends on the charge polarity. If it's a positive charge, then the same. If it's a negative charge, like in this case, you need to reverse to get FB, to reverse the direction, right? So again, this is the way you do it for this case, right? I mean, again, this is something you cannot just rely on imagination. You have to use your hand and to play a bit. So you will find out there will be a finite FB. There will be a finite FB for those electrons inside the conductor, right? So if there is a finite, let's say the net force on those electrons, then the electron will accumulate on this end, right? If there is an electron accumulation on this end, then on the other side, effectively there will be a positive charge accumulation. There will be positive charge accumulation, right? Because initially it must be charge neutral, the same amount of positive and negative, right? So now, of course, you basically need to figure out when will this charge accumulation saturate, right? When will this charge accumulation saturate? The so-called saturation, that is to say, let's say this negative charge is not going to accumulate along this direction anymore, right? So you need to stop this charge accumulation process. So how can you stop this one? So first of all, based on our analysis, if we just continue this velocity v, this fb, is it going to be always the same and always to be finite? Or it will disappear at a certain point? It will disappear at a certain time. Why? If you tell me it will disappear at a certain time, that is to say you come back to this at a certain time, at least one of them going to be zero. Which one? Which one? Electrical field? No, we are just talking about this one. The magnetic field is externally applied. Is to say within this entire space, everywhere there is this, the same constant B. So look at this formula. Is this FB going to change as a function of time? Again, we are talking about this constant velocity V. No, right? This F, as long as you have this P and V, this FP is always going to be there. That is to say, this electron, there must always be this FP, finite FP on the electron. But you still, at a certain point, you don't want to have this electron accumulate along this direction. So what do you need to do? Change the B field, of course, that is one way. Any other way? Again, now we are talking about the constant B. You need to have another force pointing, in this case, pointing up to balance this FB, right? If that happens, then those electrons is not going to accumulate in one end anymore, right? So then the next question is, where this F come from? Where this F come from? Remember, initially you will have certain charge accumulation, positive charge accumulation on this end, and you will have certain negative charge accumulation on this end. So when you have this kind of charge accumulation, you will build up basically the potential difference and also electrical field E, right? And once you have this, when you have this kind of electrical field E pointing down, then the FE is going to pointing up, right? Again, we are talking about electron, so the FE equals this Q times E, right? So also, we are talking about the negative charge, so the direction of FE and E are opposite. So then, this is going to be the FE, right? You will have this FE. And at a certain point, once this FE equals FB, then the charge, all those electrons inside the conductor is reaching a so-called, you can say, saturation or equilibrium state, right? And once that happens, you will have no more charge accumulation at these two ends. And that is the so-called the final state, right? The final state. And the voltage difference between the two ends at the final state is the so-called motional EMF. The final motional EMF you can build up between the two ends of the wire or of the conductor. Right? Still very confusing. From where? First, there's an FP. Now you just look at this one electron. Let's say you just look at this one electron inside this conductor. There is an FP should be pointing down. And if there is an FP pointing down, the electron, effectively, they are going to electron accumulation at the bottom end. So equally, there will be positive charge accumulation on the upper end, right? And when you have positive charge accumulation on the upper end, negative charge accumulation at the lower end, there will be a potential difference between these 2 points. High potential, low potential. And from high potential to low potential, there will be an electrical field E pointing down. Right? So now you create this extra electrical field E. And this electrical field E, it will apply an electrical force Fe on the same electron, which should pointing up. E is pointing down, so Fe should pointing up. Again, we are talking about electron, negative charge electron. Seems you lost here. Because here, this is the relation between these two, E and F, E and Fe. Electrical field E and electrical force Fe. Right? Until this point, is it clear? There will be an Fe pointing up. There will be an Fe pointing up, right? So now, for the Fb, because constant E, constant V, constant B, the Fb must be constant, right? How about this Fe? Let's say from at the very beginning, how and gradually how this Fe will change. It's going to gradually increase, right? Initially, again, it's charge neutral. There's no potential difference. There's no electrical field E. Then, of course, there's no Fe. And once you gradually build up this charge accumulation, more and more electrons accumulate on the lower end. At the same time, more and more positive charge accumulated on the upper side. That is to say, the potential difference between these 2 points and the electrical field E between these two gradually increase. Right? If E gradually increase, of course, if you look at that formula, Fe, it's also gradually increase. Right? So now you have this Fb pointing down, which is constant. At the same time, you will have an Fe pointing up and gradually increase, right? So then at a certain point, there will be equal. And once this Fe equals this Fb, then the same electron, the net force on the electron is 0. Then it's not going to deflect either this way or this way. That is to say, once this Fe equals this Fb, there will be no more charge accumulation at these two ends. And once that happens, that is a so-called equilibrium state. And you will keep that state forever. Right? Okay? A bit clear? And once you can figure out this defining condition, Fe equals Fb, then you have Fb, Fe, you just write them equal, and you will find out this defining condition in terms of V and B. Right? So here is just analysis we did just now. There will be an Fe pointing up, which given by this, and at equilibrium state, this is a condition, Fe equals Fb, and you will find out this is going to be the relation between E and B, E and B. And we can further write this E in terms of the potential difference, that is delta V, right? E times D. This is the potential difference, right? This is the potential difference. So in this case, the distance is just the length of the wire, L. So you will find out eventually the induced EMF is BLV. The so-called delta V in this case basically is the potential difference between these two ends. Here is the so-called delta V, the potential difference between the upper end and the lower end, right, given by this BLV. Right. And this is the so-called motional EMF. Again, you can see the underlying physical process is nothing new. It's just first, there is a magnetic force on a moving electron. And second, there will be a finite, once there is a potential difference, there will be a finite electrical field E, there will be a finite electrical force Fe. Right? Individually, all these points we have discussed before. Now, of course, everything happens in the same, and there is a relation between the E and B. And if we let's say, like in this case, because there is already a potential difference between these two, so effectively you can consider this moving conductor as kind of battery, which can supply a potential difference. So if you connect this kind of moving conductor to an external circuit, let's say this kind of simple resistor, then you will have a current flow inside this circuit, right? Effectively, now you can just consider this to be a battery. And you have a potential difference, you have a resistance, then you can get the current flow inside inside this loop or inside this circuit. Right. Okay, so next, the Lenz's law. Before I start, here you already see is something to be tested. This is something you can say it's compulsory, you must be able to do it. Is to use the Lenz's law to determine the direction of induced current. This is a so-called what Lenz's law can do. Exactly how this is done. First of all, if you look at the text statement, the so-called Lenz's law tells you the polarity of the induced EMF is always try to produce a current. So here is this delta V, and this delta V will generate a current, just like here. So this delta V will generate this I, and this I will then create a magnetic flux and magnetic field. So this I will give you this B. And this B always try to oppose the change in the original magnetic flux. there is an initial magnetic flux. So this is a so-called Lenz's law. I guess it's more than confusing if you only look at this. So let's try to break down this statement step by step. In this scenario, let's say there is this kind of a loop. This is a so-called the loop, this one. And initially, you have a magnetic flux. This is your initial magnetic flux. And once this magnetic flux is changing over time, we know it will induce a current. This is a so-called electromagnetic induction, right? Once this one is a function of time t, is not constant, then there will be an induced current flow inside this loop. So now this Lenz's law is just tell us how we can determine the direction of the induced current. So first, understand exactly the purpose of the Lenz's law. Is it not too confusing? You have a changing magnetic flux, and there will be an induced current I. The Lenz's law is just a way to determine the direction of this I. This is the purpose. So exactly how do we do it? Step one, let's say in this case, we assume this magnetic flux is pointing up and also increase. Also increase. So step one, you identify how this initial flux is changed. And two components, direction, and second, increase or decrease. So you need to figure out along which direction and also its increase or decrease. So like in this case, it should be pointing up and increase. This is how the initial magnetic flux is changed. So step one, finish. And then the step two is the Lenz's law will tell you the direction of the induced flux. And the principle is to say the induced flux should always try to oppose the change of the initial flux. Or another way to say, the induced flux always try to maintain the initial flux. Like in this case, if the initial flux is increase along this direction, so how can you maintain the initial flux? You need to have the second flux in this direction. So you can suppress this change, or you can try to maintain the original flux, right? So then the step two is to say the Lenz's law will tell you directly the induced flux should be pointing down. This is the step two. And step three, now this is the step two, you will find out you will need this kind of be induced flux. This is step two. And step three, you will need to figure out what kind of current flow will give you this flux. Now you already determine the flux. Of course, you determine the direction of the flux. You also determine the direction of induced B is the same, right? So now the final step is what kind of I will give you this induced flux? What kind of I will give you this induced flux? So now it becomes a question of determine the direction of B from I, right? It becomes a question of determine the direction of B from I. Yeah, that is how you do it. That is this. And in this case, the flux is already, B is already confirmed. Of course, you can try, let's say, in this case, you can try, let's say at this point, if you try, assume the current flow is in this direction, and you will find out inside the loop it's going to be pointing up, which is not the flux you need. So you can reverse it along this direction, and you will find out this I will give you a flux pointing along the right direction as you need. So this is the way eventually you can find out the induced current should be this direction. And this is the final objective, determine the direction of induced current. Again, step 1, 2, 3. All clear? Can we move on? Then for the another scenario, can you do it by yourself? No? Which step is difficult? 1, 2, 3. Which one? Oh, here is just, let's say, you assume the initial flux is increasing. Again, step 1, 2, 3. Which one? Let's say if you try to do it for the right side scenario. Okay, I guess, again, you have to try, practice by yourself. Follow exactly this step 1, 2, 3. And we can also actually use the Lenz's law to determine, let's say, the induced current in this kind of circuit. Whether when this conductor is moving this direction or moving this direction. Just now, if we based on the understanding of motional EMF, of course, you can determine the polarity of this delta V, and then you can for sure determine the direction of the current flow inside the loop. But we can also directly, using this Lenz's law, if the question is only about determining the direction of I. So like in this scenario, when this conductor is moving along this direction, then step 1, how is the initial flux, magnetic flux inside this loop change? The initial magnetic flux, how does it change? Again, we are talking about this moving along this direction. How does it change? Increase, and then two component, direction and increase or decrease. Yes, increase. How about direction? Yeah, into the page. So the initial flux is pointing into the page and increasing. So this is the step 1. And then the step 2, what kind of induced flux you will have based on the Lenz's law. How can you suppress this kind of change? How? Where should the induced magnetic flux pointing along? It should be out of the page, right? You have into the page increasing, then the induced one should pointing the opposite direction, right? So then the step 2, you can tell there should be a induced flux pointing out of the page. That is to say, the induced B should be pointing out of the page. This is what you can determine as the step 2. And the step 3 is what kind of I will give you this B, right? Again, you can always, typically there's just always 2 options. Let's say up, down, left, clockwise, anti-clockwise. Like in this case, if you want to have B pointing into the page, then it should be pointing out. So this B pointing out of the page. Then if you look at this wire, it should be this direction. So you can have this B pointing out of the page inside this loop, right? And you can find out this is going to be the induced I. And the opposite scenario, the same way to do it. Okay, next one is, so far we have only talked about this induced EMF. Of course, it's just like the typical potential difference. Once you have a potential difference, you will build up an electrical field E. Same thing, once you have this induced EMF, you will also have this induced electrical field E. And the relation is pretty much the same. The relation between V and E is the same, right? So this dV dx, or partial V, partial x, basically is this electrical field. Of course, here this E is the so-called induced electrical field E. And if we look at this kind of loop scenario, first we can tell, let's say if we look at there's a charge, let's say there's a charge here, there's a charge at this point. We can move this charge along this loop for one cycle motion, for one loop. And for this one loop, because there is already, let's say we assume there is already a E, there is already this EMF and also this E along this loop. Then for this charge of having this one loop motion, the work done by this electrical force should be Fe ds, right? And Fe equals this Q times E, right? Nothing special so far. And we can also write down the work done by the force in terms of the potential difference, which is this one. Right? Again, you can just consider this these two. This is just the potential difference, these two. Right? So that is to say, this one equals this one, and eventually you can determine that the induced EMF and its relation with the induced electrical field E. So far, again, looks quite similar. And actually, I think we can have a maybe 10 minutes break, and we come back for the remaining discussion. Okay, yeah, just let's continue. Here, what we have is a relation between the induced EMF and induced electrical field. And if we apply this to a simple, relatively simple scenario, is where you have this external magnetic field here, and inside there is this kind of conducting loop. And in order to determine the induced electrical field E on this conducting loop, so we apply this one, right? And if we look at this, again, particular case, you will find out from here to here. Again, for similar reason we discussed when we're using the Ampere's law, right? Always E and ds. So here is always parallel, and from here to here, E must be constant. So you can find out actually this is the induced electrical field E, induced electrical field E on this conducting loop. And if we try to build up the relation between the induced E and the magnetic flux B, phi B, then what we need to do one more step is here. Write down this induced EMF based on its definition. That is the very first formula we introduced, right? This is the formula for any kind of induced EMF. So if you combine this one, these two, and you will find out this is the so-called how we can have this induced E, induced electrical field E from a changing magnetic flux. And this is the so-called Faraday's law of electromagnetic induction. So here is just build up. Basically, this immediately closely relates to the B. So you can see again is a relation between E and B. You have a changing B, and you will get some kind of E. And this is quantified by this formula. And this is the so-called Faraday's law. So now, I'm not sure if you noticed, let's say in this case, for this one, if this E is electrical field E due to a charge, that is the electrical field E we have discussed in the first part. For that kind of E, what will you get if you do this kind of integration? Again, this is the so-called integration of EDS along a loop. What you will get? It's going to be 0. If this E is an electrostatic E, right? So actually, this brings to us the most important difference between these two different types of electrical field E. So in the first part, E, it all starts from Q. And this is a so-called electrostatic electrical field, or electrostatic field. While the E, based on this E, again, is coming from B. This E is coming from magnetic field, it's not coming from charge. And this is the so-called induced electrical field E. First of all, the two types of E, one from Q, one from B. And for the E, of course, from Q, we have this so-called Coulomb's law to determine. And for this E from B, we have this Faraday's law to determine the magnitude. So different source, different formula to determine the magnitude. And also the different behavior, mostly in terms of this integration. You do this kind of integration of EDS along a loop, again along a loop. For the electrostatic E, it always must be 0, while for this one, the induced E most of the time is non-zero. And this is the so-called one being conservative, another being non-conservative. So pay attention to these two types of electrical field E. Okay, so this is about the electromagnetic induction, and for the next topic, the so-called inductance, or self-inductance, actually later you will find out is basically it's kind of electromagnetic induction happen in a circuit, specifically in a circuit. So means you can expect the physical process is pretty much the same. It's just so far the so-called EM induction, it happens in any kind of, can be in a wire, can be in a loop, but here specifically means the induction means happens in a circuit. So for this part, the requirement is all you need to have is just some qualitative understanding of the physical picture. Again, the electromagnetic induction in a circuit. Later, you will see some formula, but in this part, you will not be required to do any calculation. It's just a general qualitative understanding of the physical picture. So again, now the platform we are going to discuss is always within a circuit. So within a circuit, of course, there will be a, let's say a battery, there can be a switch, there can be a resistor, or can be any other kind of element, right? So before we discuss the electromagnetic induction, of course, you should know when the switch is open, there will be no current flow in the circuit, right? And once you close the switch, you should know the current flow in the circuit is given by this simple formula, right? So that is to say, before we consider the electromagnetic induction, the circuit, you only have these two status, either no current or this constant current flow. Right? So now when we consider this electromagnetic induction, what will happen is the moment when you close the switch, actually it's not an immediate increase from 0 to this finite I. Before we just assume, if you let's say this is a time t, this is I, before we consider the electromagnetic induction, you just assume you have this kind of I, right? So now when we consider this electromagnetic induction process, the difference will happen basically is here. So again, you can see for sure when you close the switch, the current is going to increase. The current is going to increase, right? So the direction is going to be determined by this battery. Let's say in this case, will be along this direction, and this one is going to increase, right? So this is immediately will happen when you close the switch. So once you have this finite I inside this circuit, it should generate certain B, right? From I to B. This I will give you this B. So now can you tell me the direction of this B? Let's say this B1. The direction of B1. It should be pointing out of the page, right? And out of the page is an array of dots, right? So this is from I to B. At the same time, we know this I must increase. Then, of course, this B1 also going to increase, right? So basically, what you have is a magnetic flux pointing out of the page and increase. It's not a constant B, right? So if you have a magnetic flux pointing out of the page and increase, the Lenz's law will tell you there will be an induced B and induced magnetic flux pointing along which direction? The induced B should be pointing into the page, right? This is going to be the, let's say, B2. B1 is pointing out of the page and increase. So the B2, the induced B, should be pointing along the opposite direction into the page, right? So now, how can you have this induced B? Where does this B2 come from? Means inside this the circuit, there will be an induced current flow. Let's say we label this as I2, this as I1. There will be an induced current I2, which give you this B2. Right? Now B2, we already know, should be pointing into the page. Then you can determine the direction of the I2. That, let's say this one, the B2 is pointing into the page. So this is going to be the I into the page, right? So the induced current should be along this direction, which you will find out actually this is going to be the I2. You get I1 along this direction, I2 along this direction. You will find out they are having opposite direction. That is to say, when this I1 increase, actually at the same time, there will be an induced current inside the same circuit, which try to suppress the I1. So as a result, what will happen here is when you close the switch, the current will gradually increase instead of a sharp increase. So this is the so-called self-inductance. Again, you can see the physical process, nothing special. The only difference is everything is confined within a circuit. Right? So here, basically, the analysis we just have, so we can determine the initial I and the induced I always having opposite direction. And if we try to quantify this kind of capability, is to say the circuit try to maintain its initial position or initial status, and we can quantify with a parameter the so-called self-induced EMF. Self-induced EMF. Again, the way we quantify it is the same. So it's just still going to be proportional to this d phi b over dt. And here, similar actually for this kind of solenoid structure, where you have a series of conducting wire forming this kind of solenoid structure, and when you change the current flow inside this wire, it will also have this self-inductance. So let's say this is the initial current. This is the initial current. This is the initial current. And if this initial current is increasing, then you will find out, again, by using the Lenz's law, you will find out there will be an induced I pointing along the opposite direction. And this is always the case whether you have this I increase or decrease. If I is decreased, then this one is going to be the same direction. Again, the principle is just the Lenz's law. So here I will just skip the detailed, again, three-step analysis of the Lenz's law. But instead, we can also try to quantify this self-inductance. Again, the way we do it, first of all, nothing special. For any induced EMF, this definition applies, is valid, right? Now, because we are talking about the this electromagnetic induction inside a circuit, so this phi B, of course, it comes from B. And this B, sorry, I should. And this B must come from I. This B is not an external applied magnetic field. This B comes from I. Just like we mentioned here, this I1 give you B1. So then we can tell the magnetic flux inside this circuit, of course, still should be proportional to B, and B in this kind of particular scenario, B is proportional to I. So eventually, we can have this magnetic flux inside the circuit should be proportional to I, right? At the same time, from if we try to, let's say, quantify this self-inductance, first of all, we can tell this one must be proportional to this di dt, right? That means if the I is changing faster, then the electromagnetic inductance will be stronger. So the self-inductance will be larger. So this is a general correlation. And if you want to quantify it with a factor, let's say you can write down this from here to here. All you need to do to quantify this is you can put a coefficient between these two. Let's say in this case we can put a coefficient L. So now we have this one and this one, these two formula, and we combine these two again by definition and specifically in a circuit. Of course, they should always be the same. So you can find out this one always equals this one, right? And again, this phi b is proportional to I. So you will find out there will be this relation between the magnetic flux and this L is the so-called self-inductance of the circuit. I, of course, is just the current flow inside the circuit. So eventually there will be this formula to quantify the self-inductance of a circuit. So you can see it's as a function of the current flow and also the magnetic flux inside the circuit. So again, for those formula, for you is to understand the physical picture. Pretty much that is what we discussed here. How exactly the electromagnetic induction happens in a circuit. So actually, if you try to identify the key difference is this one. The initial magnetic flux. In the circuit, this initial magnetic flux still comes from I. But previously, this initial magnetic flux, it can come from an external magnetic field. So this is actually the main difference. Okay, so yeah, this is pretty much all we need to discuss for the magnetism and also the electromagnetic induction. So, and next, we will just, again, coming back to all the topics we have discussed for electricity and magnetism. If you still remember, this is exactly the first, if not the first slide, but still should be first, I think 2 or 3 slides, you see the so-called objective of the lecture regarding the electricity and magnetism. So now you should once understand the physical meaning of each one and also to apply this formula for some scenario to do the calculation. Again, the so-called scenario later I will be very specific. What are the scenarios you need to be able to handle? So the Gauss's law for electricity, Gauss's law for magnetism, and Faraday's law for the conversion of B to, you can say B to I or B to E, the Ampere's law for the opposite process from I to B. So this is about electricity, magnetism, and these are about the conversion from B to E, from E to B, right? So this is pretty much all about these 4 formulas. So this is B to E, and this is E to B, right? And okay, so the way we establish this four formula, the so-called Maxwell's equation, we start from the electrical charge. From one electrical charge, there is certain basic properties. The charge polarity, the charge conservation, and the amount of the charge is always quantized. So this kind of basic property, of course, you should be familiar. Basically, this is the starting point of all our following discussion. And once we understand the behavior of single charge, then we can classify material either into an insulator or to a conductor. And the only difference is whether this charge can move freely or is kind of fixed inside the material. If it's it can move freely, then we say it's a conductor. If it's fixed, then we say it's an insulator. So again, of course, we may not test you directly what is a conductor, what is an insulator, but instead, if let's say the question is given in terms of conductor, then this kind of understanding it should come into your mind. And the next one is the electrical force, the interaction between two charges. And the most simple scenario is you have 2-point charge. And this is the so-called Coulomb's law to quantify the magnitude and also the direction of this electrical force. You have 2-point charge, and from this simple scenario, we can extend to even more complicated. Let's say you have more than 2, then all you have to do is to apply this Coulomb's law for each each pair of charge. 2, 1, 2, 3, 1, 4, 1. So this is the idea of moving from 2 to, let's say, 3, 4, 5, this kind of finite number of charge. If you want to further extend to infinite number of charge, then we need to define another concept of so-called charge density. And the way we define it is just the ratio between these two. Of course, this depends on the dimension, whether you have 3 dimension, 2 dimension, or 1 dimension. The way you define the charge density is a little bit different. And here, the so-called, because very often we will need to use this the concept of charge density. So sometimes we may ask to test your understanding of this charge density in this way, to ask you to do some conversion of charge density at different dimension. And this is, if you still remember this tutorial question, where basically what you did is to convert this one-dimensional charge density lambda to 2-dimensional charge density sigma. This kind of conversion, again, of course, here the underlying concept is just how you define the charge density for different dimensionality, right? So again, you can see the two-dimensional density times two-dimensional area, you get the total charge. Or you can also get the same total charge based on one-dimensional density. In this case, one-dimensional density, one-dimensional length. So what you get should be the same, right? Both should be the total charge Q. Right? And here, there's another similar question. Ask you to convert this two-dimensional charge density to one-dimension charge density. So it's kind of the opposite. Let's say you have this kind of infinite two-dimensional charge plate, while the width is finite, but the length, let's say the length along this dimension is infinite. It's infinite. So it's a two-dimensional object, and the two-dimensional charge density, let's say, is given as sigma. Now I can, you can let's say, purposely or artificially create this kind of one-dimensional wire. This kind of one-dimensional wire with an infinite small width, dx. So effectively, it is a one-dimensional wire. But still, it has we write the width as dx. So then, what will be the one-dimensional charge density on this wire? One-dimensional charge density on the wire. Again, if you follow the same as we did in the tutorial, the total charge should be, if based on two-dimension density or based on one-dimensional density, let's say lambda, right? So now we apply this specifically to this wire. If it's two-dimension, then sigma, the area, we say the here is just, let's say the infinite width. Let's say we just read as length L. And the width of this wire is dx, right? E equals, now we look at this one-dimensional density times one-dimensional length, which is also L. So let's just put this as L, although we can put this L as, let's say, infinite long. So you will find out this one-dimensional density is just E equals two-dimensional density times this dx. Right? So this is how you can convert two-dimensional density to one-dimensional density. Again, you can see it's idea. The principle is nothing special, from 1D to 2D or 2D to 1D. And next is about the electrical field. Once we can define the electrical force, then we can further move on to define how the electrical force is generated. That is through the electrical field E. And by definition, we have electrical field E defined. We have electrical field E defined in this way, the ratio between force and charge. And this is by definition. And we can apply the formula by definition for different types of charge. Of course, the most simple scenario is single point charge, right? And you apply this general formula to this simple scenario, you will find out this is a E due to 1 point charge Q. So now you have this electrical field E due to 1 point charge Q at the location at the distance R. Right? And from 1 point charge, of course, you can move one more step to get the E due to multiple charge Q1, Q2, Q3, let's say. We can also move one more step further to get E due to infinite number of charge. And that is the so-called continuous charge distribution. So now here, basically this entire charge distribution is not a single point charge anymore. So then the way we do it is we need to purposely create this dq as a single point charge. And start from here, apply this formula only for dq. And the next step is to do the integration along this entire charge distribution. And in that way, what you get is this total E due to this entire charge distribution. So this is one way to get E based on Q. Based on Q. And when it comes to determine the electrical field E, we have a much more powerful way, that is the so-called Gauss's law. So the Gauss's law. And the Gauss's law basically tells you for any closed surface, the total electrical flux is given by this ratio, this simple ratio, Q in divided by epsilon naught. The physical meaning of this integration is just the total electrical flux penetrating through a closed surface, right? So this is the Gauss's law. Of course, again, in detail how you do this, how you apply this Gauss's law to determine E, we have been doing this in very much detail during the lecture and also even more during the tutorial. And based on the Gauss's law, we derive this some of very important property for conductor. And the first two is this. Inside the conductor, both E and Q must always be 0. And while just outside the surface, E is given by this ratio. So here, when it comes to determine E based on the Gauss's law, again, all you need to be able to handle these two scenarios: a charged sphere and an infinite charge plane. These are the only two scenarios you need to be able to handle. Of course, here the so-called, let's say I ask you to use the Gauss's law to determine E for, let's say, a sphere. Then you need to do it, follow all the steps. Construct the Gaussian surface. You need to tell me what kind of Gaussian surface. And also, you write down this Gauss's law, this equation, and step by step how you do this integration, how you determine this Q in. You need to show all the steps when I specifically ask you to use Gauss's law to, let's say, to determine E. If you just give me, let's say, the final result, of course, you will get some marks, but it's not going to be full marks. You have to show me the detailed steps. So this is about the Gauss's law. And another aspect of electricity is about the energy carried by electricity. And this is quantified based on the electrical potential and also electrical potential energy. So basically, here is the E, and electrical field, electrical potential are the two parameters of the same thing. Then for sure, there will be some direct relation. Let's say from E to V, or E to U. U is the potential energy, V is the potential, electrical potential. Again, these two are these two parameters by definition. So we follow the same structure. We apply this definition formula by definition for the most simple scenario, that is 1 point charge. So we can get electrical potential V due to 1 charge Q. We can also get this electrical potential energy between 2 point charge Q1, Q2. And from point charge, we can move on to multiple point charge, and this is the way we do it. Again, so you can see there's nothing special. From single charge to multiple charge, especially from single point charge to infinite number of charge. Whether we do it for E or we do it for V, is the same. And in terms of electrical potential, we also have this very important understanding. That is to say, for any conductor, this electrical potential is the same at any point on the conductor. On the surface, interior of the conductor is always the same. So I guess a little bit details you need to pay attention is here is delta V equals 0, not V equals 0. The potential on a conductor, whether it is inside or the conductor surface, it can be non-zero. It can be non-zero. While in terms of E and Q, the absolute value is 0. So some typical question, of course, like in this case, while we are not testing directly a simple point charge, but instead this kind of charge sphere, where the densities are given, and ask you, let's say, I can ask you to determine whether E or V, let's say at this point P. So how are you going to do it? What we already done during the in the tutorial and also in the lecture is we did it for one charge sphere, right? Let's say that is you can get E1, V1. So if you do the same thing for twice, you will also get E2, V2. But of course, how you can get this total E from E1, E2, and total V from V1, V2. And the difference is E is a vector. You need to consider the direction of E1, E2, while V is only a scalar. There's no direction for V1, V2. So this is another types of question. Of course, we can put everything inside this kind of pretty much the capacitor structure where there is two infinite, let's say infinite plate. Again, the densities are given. I can ask you to determine E, basically E at any point. Inside, outside, E, V, all the same, right? So you can see pretty much sphere and infinite plane. This kind of, these two types of charge distribution. So you need to use the Gauss's law first to determine E, and from E to determine V. Again, here, this kind of question here, I just to give you an idea, roughly what it's going to be looks like. I'm not giving you the, let's say, the exactly details of the question and also the solution. I'm not going to give you that. And another topics about electricity, actually you can just consider it to be a separate topics about this capacitance and capacitor. First, this relation by definition. Again, when we say something by definition means it's always valid. It applies to any scenario. Like here, this relation for a capacitance by definition, whatever types of capacitor charge distribution, fully charged or partially charged, this relation is always valid. Well, for this one, it's only valid for a capacitor with two parallel plates. And when you have this kind of simple capacitor geometry, you can use this to determine the capacitance. Of course, actually, I mean, for our course, we deal with this kind of simple capacitor most of the time. And the way we are going to test, actually most are related to the equivalent capacitance. And the foundation is these two types of connection, capacitor connected in series or capacitor connected in parallel. The relation in terms of the equivalent capacitance, and also in terms of the charge, in terms of the potential difference. Right. So you already see some very similar question in tutorial, let's say to determine this kind of equivalent capacitance. And the way you do it, again, in some case you may have very complicated circuit, but the way you do it is always you try to simplify the circuit step by step. And for each step, you write down the equivalent capacitance based on either this one or this one. And in addition to this equivalent capacitance, we can also, let's say, test your understanding of these two relations. And the way we can do it, basically, let's say, whether for this kind of circuit or for this kind of circuit, we can ask you to determine the potential difference between any 2 points. Let's say, like we can ask you to determine the potential difference between D and E, A and E, B and D, basically between any 2 points. You should be able to determine the potential difference. Of course, the way you do it is you will need to understand not only the equivalent capacitance, but also this relation in terms of delta V and in terms of charge Q. So again, I already mentioned when we discuss this is something also for sure you will see in the final exam. Well, for the magnetism and also magnetic force, magnetic field, first of all, we also talking about the force for one charge. For one charge. But of course now, here, there should be a moving charge. For the magnetic force to be non-zero, you should have a moving charge. You should have a finite Q and also finite V. And then this will give you the FB. And this is the formula to quantify FB, but actually equally important is to determine the direction of FB. Again, we have been doing this quite a few times. One is you do this to determine V cross B, step 1, and step 2, pay attention to the charge Q. If it's positive, then this is also FB. If Q is negative, then this is going to be FB. And for a single moving charge, we also discuss the charge motion inside magnetic field. That is the circular motion defined by this formula. Again, you need to understand the physical meaning of this formula. Magnetic force and centripetal force for any circular motion. So in this kind of particular case, now the magnetic force is serving as the centripetal force. That is why you have this defining formula. And from here, of course, you can then derive some general feature of the circular motion, the radius, the period, or angular, or this kind of angular frequency, or this kind of parameter. And from one charge, here we also make this extension from one charge to infinite number of charge. That is, from one moving charge to this current carrying conductor. Basically, here you have an infinite number of moving charge. And we can derive the magnetic force with this formula, ILB. And here, for this formula, one thing you need to take note is how we define this vector L. First, the magnitude is just the geometric length of the wire, and the direction of the vector L follows the direction of I. Follows the direction of I. So this is how we determine, define the vector L. And this one applies only, just like any other formula, only when you have all the parameters being uniform, that is to say constant I, constant L, constant B. Then you can use this one directly. If any one is not constant, then you will need to do in this way. Again, the idea is the same. If the entire I or entire wire is not constant, then we can purposely construct this tiny section ds so that both I, L, B are uniform for this ds section. Then we can apply this simple formula to get FB for this ds section. Then one more step to do this integration along the entire wire. that is going to give you the total force. And about the magnetism, first, the so-called the source of magnetic field, that is from I to B. From I to B, the way we quantify it, again, by definition or by using this Ampere's law. Using the Ampere's law. Again, the difference between these two, by definition, applies to any, in principle, any scenario. This Ampere's law, it only applies to a closed loop. So here is you need to have a closed loop. Again, when it comes to use Ampere's law to determine the magnetic field B, this is the only scenario you need to be able to do. Again, just like the requirement of the Gauss's law, here if I ask you to use Ampere's law to determine the magnetic field B, you have to write down all the steps, not just the final, let's say the final result. And in addition to the Ampere's law to determine the magnitude, equally important to determine the direction. Now we have another types of right-hand rule is you align your thumb with the current I, and this forefinger will curse along the magnetic field B. So this is the second type of right-hand rule. So here and here. So we only have these two types of right-hand rule to determine a certain direction. This one is about the magnetic force, and this one is about the direction of magnetic field B due to I. So this is a generation of magnetic field B. We also have the opposite process from B to I, that is the so-called electromagnetic induction. And again, electromagnetic induction by definition, and for a special scenario of a moving conductor inside a magnetic field. So these are the difference by definition and for a special scenario. And here, as I already mentioned, this is also something you must be able to do. Use the Lenz's law to determine the direction of induced current. Again, step 1, 2, 3. So here I will not repeat. And finally, the so-called induced electrical field to build up the relation between B and E. So here some typical question. Actually, some is already just copied from the lecture note. Like in this case, what you have is an infinite long wire where there is a current flow I. At the same time, you have this kind of rectangular loop just close to the wire. So what happens here, of course, once you have this I, it will generate this B actually in all the space surrounding the wire, right? From this I to B. So how do you determine the magnitude? Using the Ampere's law. How do you determine the direction? Using this right-hand rule. And if you can determine the magnetic field B, of course, if, let's say, in this loop, there is also another current, let's say I2, then I can ask you to determine the magnetic force on this loop, right? On each side, on this wire, this one, this one. For each side, how do you determine the FB? And you can also ask you to, we can also ask you to determine the magnetic flux through the loop. So that is B times A, right? Of course, whether you can apply this B times A directly to figure out the total flux will depend on whether you have both B and A being uniform. If yes, you can use it directly. If not, then you will need to construct a tiny section like this and then do the integration to find out the total. And for this part, actually, we already, this is exactly the part, I think, at the end of the last lecture. And we can move one more step, ask you to determine the induced current. Let's say if we can make this loop moving along this direction. Here, you already determine the flux. And on top of this, if this loop is also moving, then you can determine how this flux is changing, right? And if you can determine how this flux is changing, you can, in principle, determine, at least determine the direction of the induced current. Of course, for this kind of question, everything is integrated together, or in some a little bit simple scenario, let's say in this kind of circuit, we can ask you to determine the induced current in the loop D, whether when you close the switch or open the switch. The idea, of course, is when you close the switch, the current is increasing in the loop C, and when you open the switch, the current in the loop C will decrease. Let's say you have this I. It can be increase or decrease. Of course, this I then will generate a B inside this loop D. Depending on how this I change, you can also figure out how this B change. And from there, you have a changing magnetic field. Using the Lenz's law, you can determine the direction of induced current in loop D. Right? And another types of question is we can combine both electrical field E and magnetic field B. Let's say ask you to figure out the motion inside this kind of combined field. But let's say there can be a source charge at this point. First of all, it is accelerated through this kind of capacitor structure. Basically, what you have is a potential difference, or you have an electrical field E, right? And after a certain acceleration, we can make this charge enter a magnetic field. So once it enters magnetic field, of course, you will have a circular motion. So for this kind of question, of course, the way you do it is you will need to write down the defining equation for the process 1 and also the defining equation for the process 2. For the process 1, basically, is let's say the charge acceleration under electrical field E or under electrical potential V. While for the process 2, basically, is the circular motion of a charge inside a magnetic field B, right? So this is the defining equation for these two processes when it comes to this kind of both E and B. Right. Okay, I guess this is pretty much all for the electricity and magnetism. So yeah, then that is all for the second part lecture. And next Tuesday, I already posted the announcement. We are going to have this quiz too. And later, for the, let's say for your preparation of the final exam, for the second part, I would suggest you to start from the summary lecture. So at least you have a whole picture, the big picture, what is discussed, and also what are the so-called the key points. Okay, yeah, that's all.